Great. Well, welcome to the second session. We have three talks in this session. The first is by Professor Liu Xie from Texas A&M University, and he's an expert in energy networks.
Thank you, Stephen. It's a great honor to be here. Let's continue the theme of energy, as the previous speaker has mentioned about. And I'm a hardcore electrical engineer, so not only we worry about dollars, we also worry about keeping the lights on. So this is a joint work with cumulatively with three of my present and former students. Yang Chen, she's now at PJM. Meng Wu, she's now teaching at Arizona State. And Tong Huang, who is now a PhD student. And also Professor Nick Freris from NYU Abu Dhabi, and Professor Pierre Kumar, who is sitting here. So all the fun things that you hear about the grid are creating rich dynamics on the system. We got more and more uncertain renewable generation. That's much, much less predictable. You got electric vehicles. You got flexible demand, much, much less predictable. Everybody is talking about power electronics interfaces because all these new gadgets are interfacing from the grid using power electronics. That effectively means that it reduces the effective system inertia, so more dynamics. And countries like China or India are putting together long-distance, high-voltage AC or high-voltage DC lines over thousands of miles, connecting remote areas together. Much strong coupling, right? So I think this traditional way of model-based analysis and operation is going to be rendered perhaps less valid. And there is a great increasing need for, which is the theme of this work program, for real-time learning and decision-making. Now, what are the good news? The good news is that in the past decade or so, not only in this country but throughout the world, people have invested billions of dollars into sensors. And these sensors are just great resources for us to gain visibility onto what's going on in the grid. I'll just give you a couple of examples. The first example is the so-called deployment of the phasor measurement unit. For the outsiders, just think about it as a GPS synchronized fast sensor that is sampling at 60 hertz. Now, what's the state of the art before that? It was an unsynchronized static measurement every 4 seconds. So we're talking about orders of magnitude improvement, and more importantly, with a precise timestamp. That's very important because we're talking about the large grid. Once you have the time, synchronized, you can then put pieces together, right? And
what is being measured as the frequency?
These are measuring essentially 7 electrical variables: real power, reactive power, voltage magnitude, voltage phase angle, current magnitude, current phase angle, and frequency. 7, okay? We already have more than 2,000 in North America, more than 2,000 in China. India is going to invest about 10 billion or so into it in the next 20 years. Smart meters, that's close to your households. Everybody here living in the Bay Area get it replaced in the past 5 years. So again, for the outsiders, what is smart meters? These are 15-minute time intervals, remote readers and remote controllers to the household level. Right? So instead of doing monthly, sending an electrician check on your backyard, now you can do it online real time. Okay? So in this country, we already have more than 65 million, and similar numbers are also true everywhere in the world. So all of these sensors give us enormous amount of visibility into what's going on. Right? So this is just a snapshot of what you can see now on the real grid. We're not talking about toy examples. We're talking about the real Eastern US interconnection, all the way from Florida to up to Canada. So what you see here is the coloring is basically the frequency measurement at a particular location on the eastern grid. So as you can see, the grid was never at steady state. It's always changing, always oscillating, right? It's almost like people are breathing in and out, in and out. And the breathing is basically reflecting the frequency going up and down. And that's also a good indicator of the supply-demand imbalances across different regions. Now, it sounds like a fun video. So, okay, we put the sensors, we can see that. What's wrong with that? Well, this is kind of a benign example, which is just showing that people are just randomly turning on and off the lights and doing the usual things. But there are less benign examples, which I'm going to show you in the next slide. And that's a real problem that happened in this part of the country, on the western side of the interconnection. One generator up in Alberta started some oscillations, 20 megawatt, no big deal. But somehow, thousands of miles away, it created this forced resonance oscillation up and down for 200 megawatts between California and Oregon. Nobody had expected, okay? And this 200 megawatt back and forth, when we're talking about 200 megawatt, right? The city of San Francisco is less than, I don't know, 100 megawatts, right? So, so this huge swing created system island and blackout, and nobody had actually thought about that. And it's very difficult to pinpoint where it happened because it was thousands of miles away, up in Alberta. Okay? So these are some real problems we need to deal with. So that's kind of the theme of my talk, which is now utilizing this streaming data that is sending now to the system as control center. Is it possible to make some near real-time data-driven decision making? More concretely, what I mean is that can we know what's happening? Can we visualize those? These are high-dimensional streaming data. Power system engineers are high school graduates, which may not know all these detailed things. So can we visualize that? Can we do anomaly detection? Can we classify what kind of anomaly it is? And can we pinpoint where it happened? And then more importantly, is there something can be done? Can I do some adaptive demand response or generation redispatch or any kind of a corrective measure that I can think about? So I'm going to focus on the blue-colored points in this particular talk, okay? So what is forced oscillation? It's kind of a nice refresh thing back to the undergraduate classes. You can think about the power system as a large, high-dimensional, high-order dynamical system. And you got inputs from all the generators and all the demands, right? Think about there's some perturbation that's coming from the generation. Say there is a solar fluctuation up and down. And that fluctuation somehow meet the internal modes, some internal modes of the system, right? And that internal modes of the system created this sustained oscillation, right? Which are not necessarily well damped out. And that's kind of the situation that you saw in the you see in the previous slide, right? So this is kind of the situation that we need to deal with. We want to detect them, we want to classify them, we want to localize them, we want to make sure to get rid of them. So let's first talk about how to detect them. So one of the first challenge that for this type of streaming analytics for the power grid is this high dimensionality. I'm just kind of giving you a conceptual example, which hopefully kind of make the point. Let's say even we only have 100 PMU in the western US, right? This is already a much lower number than we saw. And let's say they just measure on a 30 hertz time interval, sampling rate. Let's say they just, each PMU, they measure 20 measurements, okay? This already translates to, 60,000 data points a snapshot and 5 billion data points a day, right? This kind of a streaming data sending to the control center, it is very difficult for a traditional power engineer to make sense out of them and to see what's going on. And this calls for the need for, the first thing we do is to do some kind of a dimensionality reduction. And the US power grid is protected under the US Energy Act called the Critical Confidential Infrastructure, which means that those data, those measurements are typically not to be shared in the public. Fortunately, at Texas A&M, we have very good working relationship with almost all the system operators and companies. So we have got about 4 terabytes worth of such PMU data that we can actually take a look at from the real world. So that's one thing we tested on all 3 interconnections in the US, Eastern, Western, and Texas. What you see here is basically the first thing we did, which is we take all the raw measurements of the PMU data. We get the principal component analysis of this PMU data. And what you see here is the horizontal axis is the number of principal components. The y-axis is the cumulative variations from all these measurements. So you can roughly think about them as the cumulative amount of information stored in the top X number of principal components. So sorry for the not very visible, but basically the point is that for a large system, 200 PMUs, 300 PMUs, you don't need that much, or the top 3 or 4 principal components has already accumulated more than 99.5% of the cumulative variance that is happening on the grid. And we're talking about the real data with all the noise, communication errors, the packet drops, and all that, right? So that's kind of a very good news to us, because then we can think about much better ways of streaming analytics to the system operators. And that's exactly what we did first here, which is we try to visualize them by showing the scatter plot, which is basically recast of the original PMU measurements from this high-dimensional original sample space into the, say, a subspace organized by the top 2 or top 3 principal components that we got, right? And because of that, the notion of time is lost. So we use the color coding to show the evolution of time. The more towards the blue is more towards the past, right? So as you can see, already there's some kind of interesting observations we can find. When the system was under normal conditions or near normal conditions, they actually reside, all the data points reside in extremely small concentrated subspace in this blue color. And immediately, now post-factually, we knew that there was a generator tripping. Immediately when the generator tripped, we started to see these points deviate from them. So how fast do we throw the points into the data cloud? We throw them into them at the sampling rate of 30 hertz, right? So we are basically seeing that almost in near real time that there's some event happening, right? And what you see on the right-hand side is corresponding to a sustained oscillation that we observed in the Boulevard Power Administration area, which is up in Washington. So you can see already one can develop this near real-time streaming analytics to do event detection. And this is just a recap and kind of a nicer view of what happened based on some of the Texas data we obtained. Okay. So we actually did a little bit of theory out of that, which is basically trying to say, in an online streaming fashion, what do we do? How do we do this? We constantly compute based on a moving horizon of window, the PMU measurements, and compute the PCA, and that's a very efficient computation. We obtain the pilot PMU based on the top 2 or top 3 principal components, right? Remember, principal components are linear combination of all the PMUs, but we want to kind of relate them to a physical PMU, so we kind of try to indicate what are the pilot PMUs, and based on these pilot PMUs, we'll do a streaming comparison of the other PMU measurements based on the correlation and the actual measurements we obtain from these non-pilot PMUs. If this error is small, things are okay. If the error is big, things are not okay. Simple as that, right? So this way we are able to detect this type of forced oscillation or sustained oscillation within a few samples of the streaming PMU data points, whereas conventional state-of-the-art method is usually relying on single channel or selected a few channels, sort of a frequency domain analysis, which is kind of orders of magnitude slower. So that's kind of an interesting finding that we got. So that's about. So that was kind of about how to do detection. We also have done something on once we know there's something happening, you can classify them. So is it an oscillation? Is it a generator tripping? Or is it line tripping? And more interestingly, we began to investigate into the next question, which is, suppose we knew that these oscillations are happening. Now the generators needs to be pinpointed. The system operator wants to find where it occurred. So that's kind of a more recent work. And I'm going to show you that in the next 10 minutes or so. So let's say, why is localization an interesting problem? So basically, the problem is as follows. How do I determine, based on all the measurements I obtain, right, the source, the problematic generator or the problematic input that create that sustained oscillation or forced oscillation? That sounds like an intuitive problem, right? Why do you need a PhD to work on this? You can ask a kid. So I have a 2-year-old. We go to the sea. We throw a stone into the water, start oscillating. So how do I detect the source of oscillation? Very simple. I just look at which one, if I have the measurement, wherever is the biggest magnitude measurement, that should pinpoint to the source of oscillation, right? Not true in the power system sense. I'll show you some counterexamples. Sorry? Right, exactly. And also, if I have this precise time-synchronized measurement, can I just compare the beginning of the change of the phase angle? Then whichever is starting to change the first should pinpoint to the source of oscillation, right? And it turns out that is not true either. So what I show you here is that the red curves are the measurements nearest to the source of the oscillation, and all the other colored curves are the non-source measurements. So both conjectures were shown to be wrong. You cannot rely on magnitude. You cannot rely on the phase angle leading factor as an indicator either. Right?
The frequency itself is changing here. Is that what you're also showing?
Which one?
The frequency of oscillation, not the instantaneous small one, but the larger fluctuations.
This larger fluctuation? That basically shows the oscillation mode. Yeah. Yes. So this is something I learned again with talking to Kumar. That's something in a different context. People work on these surveillance videos. And when you have a bunch of streaming surveillance videos, how do you kind of separate the person walking in the video from the background, right? And that's a classical problem. So a lot of people have worked on that. The key idea is that you try to decompose this measurement sequence into sort of two pieces, right? One piece kind of represents this unchanging but kind of a highly correlated spatial measurements, which is kind of the background. And the other one corresponds to the sort of a more sparse that it's kind of relate to the occurrence of this abnormality, which is the person walking. So we think that the problem of localizing this type of forced oscillation can be also thought about in a similar fashion. One can think about this low rank matrix that we observed earlier as indicator of the general trend that is happening across the entire grid. So for example, this would be the dominant dynamics across the entire eastern US. Whereas this source of oscillation, so that's another kind of a piece of engineering experience. None of two events, power system has a lot of events happening, but our conjecture is that none of two events will happen exactly at the same time, right? Let's say even you have a lightning strike here and then a tree falling down there. They never happen exactly the same time. So at any given snapshot, the hypothesis is that there will be very few, if not only one, events happening, right? And that's sort of this sparsity matrix, which represents that we'll try to decompose them into this low rank part and the sparsity part. And then whichever the sparsity non-zero element, the hypothesis is that would pinpoint to the source of the forced oscillation. Okay. So that's kind of the problem formulation. We get a streaming PMU data samples. We would like to decompose them into a low rank part. Now we can talk about what is R and what is P, and then the sparse part. Right? That's the original problem formulation, but it turns out this one, you can do some methods, for example, alternating projections, give you some local minimum, but it never kind of guarantees to converge. And we don't exactly know R and P. We can use some engineering judgment to say, okay, R is equal to 3 and P is equal to 2, and we can get some solution. But we have a little bit of a trouble getting the convergence in sometimes. So instead, we actually go to the right-hand side formulation, which is trying to say that we'd like to minimize this X, which is a sparsity matrix, such that the nuclear norm of the difference between Y and X plus the norm 1 of X with some weighting factor lambda, this one is minimized, okay? And this is a convex problem. We don't need to know the R and P, and there are state-of-the-art efficient algorithms to solve it. For example, we use these augmented Lagrangian multiplier methods to solve it. So what do we find? What we find is that this is a particular synthetic network which has 68 buses and 16 generators. So we did a lot of different resonance studies. We basically randomly perturb at different sources of generators and then see what will cause some forced oscillation in the grid. And we ask if we have the measurement at every single bus as the PMU measurements, could we localize where this oscillation occurred. So the result is that out of the 44 resonance cases, we were able to pinpoint 40 successfully. There are 4 cases that the results were not 100% accurate. First of all, that's kind of a very good, we present this to the real system operators. They were shockingly surprised. And then we look into these 4 cases that we were wrong, and we want to find out what caused us wrong. For example, the true source is in generator 3, but our algorithm was telling us it should be in generator 2. So that's kind of interesting if you pay attention to this network a little bit. As far as the impact is concerned, these 2 generators almost has identical impact to the grid dynamics. They are of the same order of size. They have almost the same electrical distance to the rest of the system. So the good news is that even though for the wrong cases, it also effectively narrows down the search space for us. So we know that, okay, once we have this algorithm, we can kind of narrow down the areas of search at least for the problems that we're looking at, right? So that's kind of another interesting finding. We're still kind of pushing forward this for larger scales and also to do some interesting, yes?
What you mean by there's a resonance case is that generator began to
inject a periodical input which causes a resonance on the grid.
Right. Now when you say detect and confirm, how do you do that? Because that was the original problem you said.
So the detection part is to utilize just the low rank property of the PMU data and then to run the PCA and to obtain this measurement error, to obtain this error between measurement and the projection. If that error is big, so that's detection.
So how do you confirm? Because here you know the ground truth. What I'm getting at is just look at the practical Alberta scenario. How can you confirm there that it is in fact that generator which caused this to happen, short of switching it off or something?
Okay, so I think you're asking about between detection and localization. There is a middle stage, right? Something like that.
No, after you localize, you need a confirmation, right? When you know the ground truth because you're causing it, it's easy.
Well, in the practical setting, what will happen is that this algorithm could narrow down these regions, Alberta region, say, okay, this is the place where it seems to be having something wrong. And then engineering judgment and engineering experience will kick in and then say, okay, looks like this generator is creating some kind of a weird oscillatory behavior, right? So that's the corrective measure part. Yeah. So this is not the end of the story. You can localize this, but then you need to also do some corrective measures. And perhaps before the corrective measure, one needs to confirm that's what you mean. Right? So, yeah. Okay, so no big deal, 2 ideas. One is that we utilize dimensionality reduction for anomaly detection. And we've kind of also utilized this robust PCA to explore the sparsity of the PMU measurements to localize anomaly events such as forced oscillation. And there are many, many opportunities for streaming analytics. For example, cyber attack is a big topic these days, and can you do some kind of a dynamic watermarking to detect such cyber attacks instead of just the physical anomalies? The answer is potentially yes. People worry about PMU data quality. 15% of the PMU data is labeled as wrong or bad data. Big number, right? 15%. So can you do some kind of a data quality correction? The answer is yes. You can also leverage this idea of low rank. not only we have PMU data, we also have smart meter data and customer data. Can we do streaming analytics for customers? We have done some pilot studies on sort of this coupon-based demand response, also generating some interesting results. Now, if we have individual customers, can I kind of build up a portfolio of individual customers and do some streaming analytics for demand response market on wholesale level? And one of Kumar's students has worked on that, dynamic system modeling, which potentially could be used for closed loop around the customers. And can we do kind of a real-time data-driven, if I have lots of these scenarios in the past, can I produce a tunable risk level dispatch and optimization on market clearing? And also we have worked a little bit on this scenario approach, utilizing the real data with some guarantees on the level of risk of violation. So I think there's a lot of interesting opportunities. I think people in this room could certainly teach the power engineers a lot about what can be done. I think it's a great forum to talk about these problems and opportunities. So with that, I thank you for your attention, and I'd be happy to take any questions.
So for both of these questions, aren't you essentially not including the dynamics? Wouldn't it be better if you had you write down the dynamics?
So for the first part, the theory part actually utilized the dynamics models to show that why this data-driven work would work.
But wouldn't you be better off, instead of just looking at the output and then doing the PCA, essentially looking at, let's say, linearize the dynamics, write down a measurement map, and then do the PCA on the observability gradient, which basically tells you which modes are, instead of just looking at the time sequence and then doing.
We did that also. We have two kind of observations. Number one is that it's much slower. And number two is that these modes, because of operating condition changes, is kind of hard to track. There's not a single linearized dynamical model to start with. So it's kind of always changing as the system operating conditions changes. And then the third point I want to say is that even this simplistic approach seems to be working quite well. But I think there's untapped potential in connecting perhaps some kind of a coarser model of system dynamics with this kind of a data-driven approach to say something insightful. Yeah.
So along those lines, on the second part then, if you sort of use linear dynamics and the network structure, then maybe you can turn it into an inverse problem.
Perhaps, yes. And people have kind of tried that also, yeah. And
look at the pseudo-inverse of the Laplacian and the Green's function.
Right. Yeah, that's an interesting idea, yeah.
So after computing this fast matrix, it has oscillations at multiple locations. How do you locate the source?
So basically, as far as the result is concerned right now, again, it's still in progress, but all the results we have so far have either one non-zero or two non-zeros. So we kind of just label either the one of them or two of them as the sources, and then we'll just do some further engineering judgment and narrowing down searches. Yeah.
Following up on the first question, I found it surprising that you don't distinguish between space and time.
Mm-hmm.
There's an underlying dynamical system, and so the measurement matrix should be somewhat triangular. There's a fault, it spreads one bus after another, and you're to only do the sparse and Lorentz decomposition, but there should also be some causality argument in there.
So we did both in a sense. The measurements that we obtain is kind of already showing this electromechanical kind of oscillations on the grid. And the low rank property essentially indicates that perhaps this is well justified by the swing equation dynamics on the system, on large systems. So in some sense, it's sort of the space aspect is illustrated through this large high-dimensional data. The temporal aspect, I think what it indicates is that this type of PMU measurements illustrate the dominant modes on the swing equations, but not necessarily the entire rich dynamics that you would have written, for example, thousands of dynamical equations. Those are not necessarily represented in these 30 hertz or 60 hertz measurements.
Okay, let's thank the speaker again.